Well, I'm happy to hear that everyone is able to do things, was able to do the tasks. But again, it's always good to hear what you did, okay, because for this this program, it's not so much about doing it right, but about sharing and learning from each other. What you could be something that you have researched on that none of the other folks have researched on. That's actually even more valuable because for the most part, you know, just doing it right is not sort of the intent. But anyhow, we'll continue. Today we're going to be wrapping up the task-based um, kind of format. The next one is going to be dedicated to questions, presentations, hearing what you guys think about the course. So this course has been run 3 times. Um, Anirudh Agarwal, who created this course, a senior mechanical engineer at Galamad Aerospace, he already run two sessions or two seasons, I guess. Okay. And so would love to also be able to discuss to hear from you guys, like what could have been something that you would have loved to see in this course as we prepare for the next run, right? So this is our third one. And so next time there won't be tasks like these, it will be more hearing from you. Okay. So there should be more of you talking than these other sessions. All right. So we start with aerospace and uh, astrophysics. Okay. And just to have these in mind that these will be the things that we'd like for you to explore more afterwards. Okay, we want you to be able to understand basic definitions and to describe them in your own words with respect to subsystems. So for the aerospace, we will talk about subsystems of a satellite. Okay, I'll describe the key subsystems. Um, and then we'd like to for you to be able to describe the meaning of 3 or 4 most common features for each subsystem. And then to make a simple table that lists out the some companies that um, maybe not all companies, but some companies that provide satellite subsystems. Um, the I will also give you a website where you can actually search for subsystems that we'll be talking about here. Okay. This is just to understand what is happening in industry. Okay. So a satellite is primarily divided into two things, payload and what's called a satellite bus. Okay. Galamad Aerospace, as a company, our focus is to build the satellite bus. And the satellite bus, what it really means is everything but the primary payload. So, for example, there are satellites that are dedicated to taking images. The camera itself, plus the processor that is processing the imagery and all that, we call that payload. Okay. Then the rest of the satellite, we call it the bus. So often you can actually swap out the payloads. Instead of having a camera there, you could have a magnetic field sensor. Uh, um, you could have a science experiment. You could have a variety of things. So for us, as I shared last time, I'll have many of those payloads on our satellite bus. Okay. And what we want to enable is to have maybe 10 schools, all of them building some small sensors. We carry all of them to space, allowing them to get to space in a much faster, much cheaper way. Okay. But the satellite bus itself, it has a few subsystems. Okay. And these are the ones that we'll talk about today. Okay. Um, when we talk about satellite subsystems, they are physically distinct, but often there is some overlap between them. So take this as a crash course into the different subsystems, but also understand that there is going to be inevitably some overlap. For example, there is a system called command and data handling. So command and data handling, really, this is uh, a primary computer on the spacecraft. Its job is to coordinate things such as when to point somewhere, how to point somewhere, and all that. But you can see that because it is a computer that need to be in an enclosure, for example, that there will automatically be need for a mechanical engineer to be involved, for example. So even though this is command and data handling is primarily programming, a firmware engineer or so-called embedded programming engineer, that would be the primary person for this subsystem. But in reality, you would be interacting with other subsystems as well. Okay. So these divisions are there to just help us as engineers um, structure our work and get things done assigned to somebody and so forth. But in reality, there is quite some overlap. Okay, but here they are. So command and data handling. This one is primarily to do with um, oof, my settings here are. Just give me a moment. I open a different. Okay, so the command and data handling system, again, this is a very high level overview, but it gives you all the information that you need. It goes by different names. Sometimes it's called onboard data handling subsystem. Sometimes it's called just onboard computer and so on. But just think of this as the core computer for your mission. So the entire program or application for your mission is on this device. Okay. And sometimes it is separate from another subsystem here that is, uh, in our case, we call it primary spacecraft computer. I'll talk about that in a moment. Okay. But just think of this as the primary computer for your mission. Okay. And the skills required to be involved in this subsystem are primarily firmware engineering related, which means that programming using C or C++. These are the skills needed for this. So when you see videos or, for example, um, something landing on Mars, okay, or on the moon, these rovers that you're seeing moving on the surface or actually landing, often most of that code would be on this so-called command and data handling subsystem. Okay, so it's a very important subsystem, and it's one of those that you triple check, so to speak, to make sure that everything is working as expected. Because as you know, on Earth, if something is wrong with your computer, there's a chance of, just press the button and reset. In space, it's a bit more difficult. We actually have mechanisms in space to still do restart. Okay, for example, we have what's called a watchdog timer, and this timer can it's almost just like a clock. If the clock reaches a certain value, we say reset everything. Okay, so there are some mechanisms we have in place, but generally we want to write code that is as near infallible as possible. In other words, it cannot hang, it cannot be unpredictable. Okay, so that's command data handling. The second is called communication subsystem, and the communication subsystem um, includes two main things. There is uh, the electronics part, and then there is just the physical antenna, which is a wire for communicating. And the wire really, depending on the frequency, it can be as simple as um, just a piece of wire, like literally, um, like this, okay, like something like this that you can literally just hold in your hand. Okay. So for our current mission, for example, we have a UHF antenna, and the UHF antenna, what we're using is just a tape measure. The literal tape measure, for those of you who have done some engineering, the tape measure is for just measuring distances and lengths. We cut that to the appropriate length, and it's an antenna. On the other hand, antennas can also be very complex because there are some antennas that are used to do directional pointing. Okay? Either way, antenna plus communication system, this is another very important subsystem. Of course, every subsystem is very important, but there are some that are critical because, for example, for communications, if it doesn't work, there's no way for us to talk to a satellite. So imagine you're landing on Mars and there's no way for you to talk to your satellite. It becomes a waste. Okay. Um, Now, the communications subsystem itself, it depends on the um, it depends on the frequency that you would want to transmit on. So in some cases, it can come as a communications payload. That is to say that the actual payload for your mission might be just the communications device itself. So this is actually the case for our case in the current mission that we're building. Our own X-band transmitter is the payload. Okay. Besides the other payloads that I'm talking about, we are kind of bringing other people to be on the satellite. But for us, our main payload is the transmitter or the communications device. And one of the most common use cases for satellites is actually TV broadcast. In that case, the communications device itself is the payload. So it is both the subsystem as well as the payload for your satellite. Now, the where TV broadcast works is that you actually have two separate communications devices, one that is dedicated to receiving the information or the movies from the ground, and then another that is dedicated to sending it to people's homes. Okay. But either way, these are all communications modules. Okay. So that's the second subsystem. The third subsystem is called electrical power system. And in today's world, the main way that we generate electricity in space is through solar panels, converting light into electrical energy. Then we store that in chemical batteries. Now, one of the things that as a company we're working on is to be able to store the energy in a spinning flywheel. Okay, so we have the solar panel. Instead of storing the energy in chemical batteries, we store the energy by spinning up a flywheel. Because you know, in space you've got vacuum. So if you start spinning your flywheel, and then you remove the power source, the flywheel will keep going for quite some time, and we can take that energy out to power our system. So this is something that we've started working on conceptually, in conceptual designs and all that. The reason for this is because chemical batteries, they when you charge and discharge them, I think you can notice with your own phones, for example, after a certain amount of time, this phone doesn't hold charge as well. And so for space, it's even worse because in space, especially when you're in low Earth orbit, in the astrophysics section, we'll talk about the orbits in a moment. But low Earth orbit means that you're close to Earth, between 200 and 1,200 kilometers. You actually see the sun rise and set over 15 times or close to 15 times a day. And so what actually happens is often you have to charge each round. And so you're charging 15 times a day. If you were to do that to your phone, to repeatedly charge it to full and deplete it 15 times a day, it probably will last less, just a couple of months. So we actually have the same problem for satellites, whereby because of the fact that we charge and discharge quite frequently, we end up having a problem with the mission life being shortened because the batteries themselves, the capacity is depleted to a level where charging to full is really not full anymore, and so on. So that's why, as a company, we're looking at this flywheel storage system. Okay, so it's not out there in the world yet. It will take us a few more, a few more designs to get it right, but we're excited about that possibility of just mechanically. This is quite a mechanical way to store energy instead of the chemical way of storing it in batteries. But electrical power system, um, a pretty important system as well. And for now, what we're looking at is um, this is what we're looking at. That is to use something related to nuclear power would be one of the best ways to build satellites to store or generate electricity. The problem is that actually in today's world, nuclear power is I think it's less and less a taboo since the last couple of, I'd say maybe the last decade or so. People are starting to really look into it as an alternative source of energy for environmental reasons and all that. But there is not a sufficient research for someone, at least a new company to go into it and use it to generate electricity or something like that. But as a power source, nuclear energy is by far the best for space, okay? Because it is very, very energy dense. And space, as we have mentioned in the past, one of our biggest concerns is we don't have enough volume, we don't have enough mass because it's expensive to go up. So in maybe 3, 4 years' time, we expect that Galamad also will be looking into actually deploying nuclear energy sources as part of our electrical power system. Okay, so for now, though, it is what we have right now is solar panels plus batteries, and we've just innovated on the battery side, whereby we're using a chemistry that hasn't been used, which is lithium iron phosphate. So not ION, but IRON, In other words, the metal, lithium iron phosphate, that gives us a slightly longer life. Okay, the other subsystem is a propulsion system, and this has to do with generating small amounts of thrust, which allows us to point um, either to change how we're pointed or to slightly change our position or where we are in space. Okay. So the thruster that I mentioned a few weeks back um, is part of this propulsion system. Feel free to interrupt if you were not clear about anything. Then thermal control. Thermal control itself is not a subsystem per se. In other words, not physically distinct. It's that thermal control is a subsystem in the sense of every one of these other subsystems need to have thermal control mechanisms or systems. For example, the electrical power system would be generating quite a bit of heat, okay? Because, for example, you might be getting 24 volts from an input from the solar panels, then your batteries might be at a different voltage. Then you need to use some electronic components to either to boost your voltage or to bring it down. And often these processes generate quite a bit of heat. And so somehow you need to take that heat away to a larger surface that is exposed to the outside world so that the energy is distributed across a large surface and it is radiated. So we have to think about each of the subsystems and say, okay, how do I ensure that thermally I am within the temperature, uh, um, boundary points that we have decided. So for example, for our mission, we want to make sure that everything is between minus 20 plus 120, okay, something within that range. So if something goes up to 160 or gets too cold, then we have to find a mechanism to get that heat away or to get heat to it. So as an example, for batteries, um, the battery chemistry that we're using, it doesn't work well if the temperature is too low. So what we actually have designed, we have just a very thin heater, okay? It's like tape, that level of thinness, okay? And this, we're going to supply a current to it. It will heat up the battery. So when we're on the cold side during the night, for example, we would heat up the batteries. So we have an electronics device that measures the temperature continuously and says, oh, it's getting too cold. Then we supply current to heat it up. So that's thermal control. So in other words, it's not a system by itself. It's more of a system in the sense that it touches many of the other subsystems to make sure that we can have things operate within the temperature ranges that they can operate in. So most components in the world actually have a temperature range, and you have to know about these as you're designing the satellite. The other system is called attitude control and guidance, navigation, and control. Often these are combined, and in our setup, we also combine them to call it attitude determination and control system. Last time I spoke a little about this in the context of magnet talkers and reaction wheels and all that. So this system, I think, is going to be one of the ones that you'll come out of this knowing a bit more about. So I think I'll skip that because I'll talk about some of the parts of it as we go. But essentially, it's a system primarily for pointing, okay? Not for changing position, okay, but for pointing. So think about this as two different things that if you want to move the center of gravity of a system, you're talking about a much more difficult endeavor than if you want to spin about the center of gravity, okay? So spinning about the center of gravity is mostly about attitude determination control system. But when you want to change position, for example, in space, then now you're talking about moving the center of gravity of the system. And that requires usually a lot more energy. Then the other subsystem is called structures, thermal, and mechanisms. Okay. Now the structure itself is just the physical scaffold, not scaffold, the physical skeleton or chassis that holds the entire satellite stuff in place. So the subsystems we're talking about here, they need to be held in place. The whole structure itself or the whole satellite itself, it needs to survive the launch. And therefore, to do that, it needs to be structurally strong and all that. So there is a subsystem that is called structures, thermal and mechanisms. Again, the names are different depending on the company. For us, sometimes we say structures and trusses. Sometimes we combine structures with the thermal, for example. So in our case, the way that the work is actually distributed is that the person working on the structures is also the person that handles the thermals. Okay, is also the person that handles what's called mechanisms. And the mechanism are things like the solar panel deploying. Okay. So we have the solar panel that is body mounted at the satellite, and we have a solar panel that is deployed to increase the amount of area that we are exposed to the sun. So this is a primarily mechanical engineering task, structures, trusses, mechanisms, and thermals. And mostly the software where you do the CAD modeling of the system, for example, often would also have the ability to simulate thermal distribution within your system. And so temperature distribution within your system. And so often it's the same person or same team. Okay. Now, for specifically for missions that have people on board, or people or animals or living things on board, they would also have a separate system that is life support. This is a complicated system would that can be seen also almost as a satellite within itself. So it also would have a communication system. Often it would have its own backup power. It would have certain protection mechanisms so we would escape, for example, should something go wrong. It has its own thermals, very, very stringent requirements that it has to meet, for example, right? Because you don't want the temperature to get to 120 with people inside and all that. So this is not a system that Galamad is currently building, but just to let you know that there is this very important system, especially when there are astronauts or animals involved going to space. Okay. Now for us, we have some slight changes in terminology just um, to make sure that we are not just naming things because other people name things. We felt that, for example, the onboard computer, this is the most common name in the industry of this system called CNDH. It's often called CNDH or onboard computer. Onboard computer is very common. But for us, we chose the name of primary spacecraft computer because to us that makes it very clear that this is the primary spacecraft computer because actually on the satellite there are actually so many computers and all of them are on board. Okay. So in the past, when the satellite industry was very small, perhaps you very young, you had just a few key computers because at the time, of course, computers were very expensive, and so it made sense to say onboard computer. Everybody knows, but now the term onboard computer is kind of a misnomer. And then, as I mentioned, the ADCS is the one that combines attitude control and guidance, navigation, and control. Okay. The thruster is a propulsion system, and then we have specifically deployment mechanism for deploying the solar panel as well as deploying the antenna. So for us, like, we have a tape measure antenna that is folded. Then when we go to space, we deploy it. So this is something that we have designed in-house and we have tested uh, the deployment mechanism of the UHF antenna. Okay. Okay. So the task for the aerospace people is just to look into this subsistence okay, from like I've said, there are so many ways to talk about these things. Which do you understand are the core subsystems for a satellite? Okay. And then you can, by core, I mean that, for example, I've said this is separate but technically this and this are the same, right? So we would like just for you to, in your own understanding, based on what I have shared and based on your own research, just say, okay, from my point of view, the core that should be there in every satellite should be this, and then you can give some reasoning around why. For example, if you think mechanisms need not be there, for example, you can share why. And it is true, there are actually many missions that don't have a deployment mechanism. But just to firm up your understanding to see what is extremely critical to a satellite and what isn't. Okay. So you define the all the core subsystems using a satellite and you describe the main features. So the main features, for example, when we're talking about onboard computer, what is important, right? You would find that, for example, how much RAM it has is important, how much storage it has is important, the speed that it has is important because this is a computer. So in the same way that you're choosing a computer here on Earth, a computer for gaming versus a computer for just I don't know, Word and PowerPoint would be different. So in space, you just also need to have that. So you just describe what are some of the common things you look for when choosing each of the core subsystems. Okay. Um, and then we have some reference notes here. You look, once you receive this, you'll be able to see some of these companies and what they're building. Okay. So that's all on the aerospace side. We'll now move on to the astrophysics segment. Okay. And today we'll talk about some orbits. In particular, we'll talk about sun-synchronous orbit and geostationary orbit. I'll also mention low Earth orbit and very low Earth orbit. So I'll share what those mean and why. What are the orbits used for? What is the Molniya orbit and why is it used? These three or four examples of satellites in each kind of orbit. And these three or four examples, you can get these from the same link that I shared last time, where you can view all the satellites that are in space and that have been launched recently. If NY20 is code, N2Y0, N2, excuse me, N2YO.com. Okay. So there you can see a lot of satellites. So there you just check out, once you understand what Molniya orbits and all these things, you can do just a quick search of which are the satellites that are in any three or four examples. Okay. Okay. So first is the sun synchronous orbit. Sun synchronous orbit, really what it means is that it is synchronous with the sun. And the literal meaning of that, or the practical meaning of that, is that if the satellite passes over Mumbai at 10:30 today, it will pass over Mumbai at 10:30 tomorrow. It will pass over Mumbai at 10:30 the day after, and so forth. Okay. So this orbit is very important for comparisons, because if I want to compare, for example, pictures from yesterday to today, taking a picture at 10:30 yesterday and taking another picture at 7 p.m. today, you compare these two, you'll be misled if you see differences, right? You'd think it's because maybe there was a flood when in fact there wasn't a flood. It's your picture that's problematic. So for many applications of image, in terms of, especially for imagery, they use this sun-synchronous orbit in order for comparisons to make sense. In other words, all other factors have become, I guess, unimportant, because you're making sure you do it at the same time. Of course, there are still minute differences, because at 10:30 today, there may be a cloud over my place, then tomorrow there isn't a cloud, and so forth. So there's still some algorithmic work that needs to get done, but it's far easier than if I was taking the picture at different random times each day. So sun-synchronous orbit is by far the most common these days. So for us, for example, for our satellite, we are very likely going to be in a sun-synchronous orbit between 500 and 600 kilometers from the manifest that we've been given so far. And so just think of this as an orbit that allows you to do things in a predictable manner at a predefined time. So a very common orbit. Another orbit is geostationary, and geostationary just means that it is stationary relative to a position on Earth. Okay, so the specific distance from Earth is around 36,000 kilometers, okay, or around 22,000 miles. At this distance, the satellite is still moving around the Earth, but the Earth is spinning at a velocity, also spinning. Of course, the Earth is also spinning. So the two speeds match, or they're they're relative to each other. The effect is that the satellite does not go out of sight for you. So most of TV stations that you use satellites, or most of the satellite industry's TV broadcasts, are from geostationary, because that allows you to just put your dish above your house or on a wall on your house, and that's it forever, so to speak, because satellite doesn't move much. Okay, so this is very useful for TV broadcasts. Okay, and you can check out this link to see the many satellites in this orbit. Okay, there are unconventional orbits like Molniya orbit, star orbit, and other types of orbits. But in particular, I'll talk about Molniya orbit. This particular one is um, it is very long on one side and very short on the other. So you see this particular one here, the satellite over here. it's very close to Earth. And then it goes the other side, it's very, very far away. And this is useful for, let's suppose that I'm interested in being, so you know that not everybody is near the equator, for example, right? People up north, very much up north, actually, if they were to launch a satellite and they wanted to be in geostationary orbit, it's actually not an easy thing for them, okay, because they're over there. Okay? So the geostationary orbits there, the geostationary orbits, they're equatorial, primarily equatorial. So for the folks who are up north or very down south, what they do is they use this Molniya orbit. This is primarily used by the Russians, actually. This almost is close to geostationary in some sense, in the sense that you'll be above here for a long period of time, and then very quickly you pass the other side. So because here you're very close to Earth, your speed is very high. So it's like you could spend maybe, let's say, 3 hours on this side, then on this side maybe like 36 minutes or something like that. Okay, so it's an eccentric, highly eccentric orbit, and also an orbit whereby you do it in order for you to simulate. In order for you, so you design it so that you can be above the location of interest much longer than anywhere else. Okay. So if my location of interest is India, for example, I'll design the lunar orbit so that when it's above India, it will spend the largest amount of time, and then anywhere else, it just zooms past, and so forth. Okay. So this is an orbit that, again, currently has been mostly used by these Russian satellites. Okay. But it is, again, it is not too important for other people, like for those of us who are, say, in Singapore and this belt near the equator, there's not much need for Monia orbit. Okay? So that's one special orbit. Okay, but I invite you to take a look at the other orbits and then complete the tasks that are over here, which are just to be able to talk about the different orbits and why they are used, and then some examples of satellites in those orbits. Okay, so we'll end here for the aerospace and astrophysics track in order for us to have sufficient time to go into the other mechatronics and coding tracks. I can take one question if there's someone with a question. Otherwise, the folks in this track can bow out.
Any questions or doubts, anyone?
No, sir, not yet. Thank you.
Great.
No, sir, thank you.
No, sir. Thank you.
All right. So I think now the folks in here are for mechatronics. So okay. So for mechatronics, the objectives today are going to be to look at the equations for the magnetic field, specifically for the magnet torque, to determine the relationship between current and magnetic field as uh, when we measured using ammeters and those kinds of devices, get the relation between the magnetic moment and field in order to be able to verify the measurements. And then we'll provide you some links so that you can use those to write some explanations for what we're going to discuss very quickly today. On the coding side, we want you to be able to implement some field versus moment equations, and we're going to provide you a template to starting code for this. Look at 2D arrays and object array codes for more complex implementations based on the starting code that we'll also provide. And then just for you to understand 2D arrays and how to get items out of the array, how to put items into the array. The specific case that we're sharing with you here, of course, is aerospace, but we think that it's an important skill, no matter where you are, to be able to understand 2D arrays. Um, so the magnetic field of magnet torque is just the magnetic field of any we start with the magnetic field of any current carrying wire. Okay, so this equation shows you the magnetic field of any current carrying wire, whereby this is a constant. By constant, we mean that we've agreed on its value as scientists, and this is the current. Okay, and then this is to do with the length, and this is to do with the direction. Okay, now the magnet torque that we're building, for example, the magnet torque that we're building is something like might be 2 cm, for example, right? So might be very small. This number might be very small, and um, excuse me, the diameter of the wire itself might be much smaller than 2 cm. So there's the loop itself, and then there's the wire that is carrying current itself. So the wire itself is just 0.4 mm, for example, in our case, like not 2 cm, 0.4 mm. So very, very small. Okay. Now, the field for a current carrying wire distance, there's another equation there. This is specifically, we want to know, for example, here, what is the magnetic field here? Okay. Not just at the core, not just around it, but at some random point chosen anywhere. So in this particular case, we are able to use an equation of this type. Okay. Um, Now this equation. I mean, what it gives you is essentially a 3D value. Okay. Something to do with the magnetic field in X direction, magnetic field in the Y direction, magnetic field in the Z direction. As you see, this notation here, it means that it's a vector. Okay. And this is actually a cross product. So cross product of these two also gives you a vector. And so there's actually a rule, they call it right-hand rule, to help you tell the direction of where the current is going to be, direction based on the current, and based on the direction of current, as well as most of the direction of current, because this is called a right-hand rule for the particular case of the this is my wire. If this is my wire going through my hand, then I grab the wire like this, and I should be able to tell the direction of north and the direction of south and so forth. So in other words, those are the base principles that we use even for our case as we're building the magnet torquers. Okay, so for the magnet torquer, the R is very small. In this case, they use 4.75 mm. Okay, so not 2 cm. But Z can go from 3.5 to 106, 106.5. This would be the length of for example, the length of the entire magnet torque, for example, right? And so we provide you some initial values using Excel. You will see those values after this lesson. But essentially, just for you to explore, to change some numbers in this and see the magnetic field change. So, for example, if you change the R, you should be expecting that if you decrease the R by twice, or you halve the R, you should be expecting a quadrupling of, let's say, the magnetic field. So it's just for you to play around to see that the theory matches what the code does. Okay. So the calculations using Excel, you see something like this. Again, the Excel file itself will be provided to you, but just quick explanations. This is like the distance. And as you see that the further you are from the magnet torque, okay, this is distance. The further you are from the magnet torque, the lower the magnetic field. So you're going from -5 to -6, okay? So in the Excel file, you just drop in some other values and confirm that this is indeed what's happening, okay? So you get some Z values in distance in millimeters, and then you see how the values of B change, okay? The unit that's mostly used is Teslas. If it's very small, nano Teslas. And for even when we're in space, actually the magnetic field is still quite weak. Okay, so we're still talking nano Teslas. On Earth, the magnetic field is a bit strong. We're talking micro Teslas, milli Teslas, which is pretty big. Okay. So in the case of the value from the Excel sheet, we should expect something in the vicinity of 400 millitesla. Okay. Now, we supply a current of 0.5 amps in our wire, for example, right? If we supply 0.5 amps and then we multiply that by, so in the previous equation, you see there is mu, which is a constant, then there is I, okay? And then um, this this whole portion, know, um, that becomes that, and then together we're able to get a magnetic field of the torque. Okay, so there are two things here. Okay, there is the wire itself. There's the wire, just the wire itself, which is carrying the current. Okay, and then there is the fact that wire is looped around something. Okay, so these two things come together to give us the magnetic moment. So even though the wire itself, when the wire is going around, the magnetic field is actually around this wire. But when it is looped around our core, man, the steel core, right? The magnetic field itself will have a north pole and a south pole along the core itself. Okay. So there are two maths that you're going to be exploring in this exercise. There is the math of just the wire itself, and there is a math of the whole magnet torque, that is a coil around a core. Okay. So measuring the magnetic field, the magnetic field itself is a process that um, requires one, it could be like for me when I was doing the experiments for this magnet talker, I just use my phone. So I bring my phone close to the magnet talker, I check the magnetic field, and then I remove the current and I check the magnetic field, or vice versa. I start with measuring the magnetic field in the ambient environment. I turn on the current, then I check the new magnetic field. Then I know that any additional magnetic field is due to the uh, magnetic field that the magnet torque has created. Okay, so we use these simple experiments, these simple measurements to get us a sense of what the magnetic field is being generated. Now, magnetic field um, itself is not magnetic moment. Okay, because magnetic moment is a function of the magnetic field and the you know in a bunch of other things come into play for us to get the magnetic moment. So in our discussions with customers, for example, we don't actually say that our magnetic field we generate is this millitesla, for example. No, we actually say we're going to generate for you 0.4 amp square meters, for example, okay? Because that moment can be more easily used to choose with a magnet torque that is sufficient for their system, okay? So that's why here we talk about magnetic moment being a function of the area, and then we uh, when we say, for example, 0.4 amps, 0.4 amp square meters for magnetic for magnetic moment, um, we we just mentioned that number, but that could refer to a different amount of current, different amount of voltage, depending on the overall system design. So in this exercise, one is just look into the magnetic field generated by a wire, then the magnetic field generated by a magnet torque, and then finally to explore the relationship of that to magnetic moment. Okay. So you'll understand a little bit more as you look at this code. So the code is made available. Just need to understand line by line what is going on. Why are they multiplying like this based on the equations that I have shared? Okay. So um, here it's just um, you know, again, basically, I think it's better if you explore this yourself. But quickly to share what's going on here is that we're using a library that we've used in the past, which is NumPy, to do some mathematical manipulations. Okay. All of this code, the goal is just to calculate, okay, what is the B? B in this case being the magnetic field. Okay. So we change a few parameters, then we look at, okay, what is the B that we're calculating? Okay. So Excel is also a powerful tool for a start, but depending on how comfortable you are with Python, it might be easier to do with Python. So in this particular case, we've given you both Excel and Python. Excel for quickly just changing some value in a cell and then you see the effect. And then for Python for implementing it in a manner that is again, Excel itself is not like engineers don't use it. They still use it. We still do use it. It's just that sometimes if you want to share your code with somebody else and they can run on their computer and link it to other programs, Python is better. because they don't need to import an Excel and get complicated. So that's why we would like for you to look into both the Excel, to look at both the Excel as well as the Python. Okay. Again, the code will be provided to you for reference. Okay. Are there questions on the coding part?
No, sir, it was clear.
So you get the Excel and Python files. Okay. Um, and some of the things that we're going to explore in this in this coming or you're going to explore in this coming week are found at these links, which are Anirudh's GitHub, and you see that he has detailed explanations for things. He's got a few files there that to help you understand uh, what is happening. So a lot of files there. Okay. And not everything is important. I'll share this task tomorrow to make sure that you're not going all over the place, just to clarify specifically what we want you to do. Okay. I but it will be useful for you to show. Okay. But we just made this available to you guys to be able to look at the broader picture of 2D arrays and creating 3D graphs and all that. Okay. Um, So for coding, we'd like for you to understand the implementation of arrays and objects, to understand the plotting of 3D graphs. And 3D graphs means, for example, we have the Earth, the 3D shape of the Earth, and the satellite around it, for example, right? Those kinds of graphs. For Python, often most things that you will be doing, especially when you're starting out in Python, would already have been done by somebody else. So the important thing in Python to understand is to know the Python package index, right? pypy.org, where there are libraries for you to use to do anything. So you can start with, ChatGPT or some other place. I'd like to do this. What libraries can I use? Then you install them and use them. So when we say that understand the plotting of 3D graphs, we don't want you to go, it takes years of understanding 3D math for you to do it on your own. What we're asking is that you find some libraries and draw some 3D graphs, and would recommend that you draw something to do with this course, which is, for example, an Earth in 3D with a satellite around it, for example. That would be sufficient. Okay, and then try writing some code, object arrays, um, how to get numbers out of a 2D array, how to put numbers in, how to maybe add them, concatenate them, or do some mathematical manipulations with the arrays. And we've also provided some resources for specifically for coding. Okay. Um, there are many resources, and as it is today, as for us as well as for seasoned engineers, it is better to start with some level of LLM. At the same time, we see it very clearly that if you really want to use LLMs in the most efficient way, you have to yourself know what you're asking and what you're doing. So even though in these kinds of sessions we recommend ask ChatGPT or that, it is not to say that you don't need to learn. You don't need to go to these websites to learn. It actually, you would be a very ineffective engineer if you just use ChatGPT throughout. Okay, but if you use ChatGPT in a strategic manner, for example, recommend some libraries for me to do 2D array manipulation. Okay, because you need to know these libraries. So we recommend a balance between you doing some work and leveraging available tools. We don't want to say I never use ChatGPT and all that. It's not, it doesn't make sense these days. You have to kind of use it. At the same time, for you to know if code is good, actually it takes understanding. So that's why we're saying you should look at traditional resources of learning Python and combine that with novel tools like ChatGPT. Okay, so this is for coding. Okay, and then as I mentioned for uh, mechatronics, the tasks remain the same. Just some these equations that I've explained. Just look into them understand what each term is doing, okay? And then using Excel or um, you, on your own, just look at how you would be able to, for example, if you change the R, what happens and so forth, okay? That is that is for you in the mechatronics area, okay? And the links, when I say the links provided, we have these links, okay? Where there's a few more explanations about what each of these symbols mean. Okay. Okay, I'll stop there and await any questions from folks on the call.
I have no questions.
No questions, no doubts, all good? Great, then I'll be sharing with you all these files. And next week, this is the final week of the internship. So next week, you guys have to present what you have done, right? Great. So I guess we are good to go, Christopher. Thanks for the session. Thank you, everyone. See you next week for the final session.
Okay.
Yeah.
All right, thanks. Have a nice
Bye.
evening. Bye-bye.
Thank you, sir.
Thank you, sir.